why it's thinking. All right, so for this focus question, if I had these, which I don't really drink sodas, but let's say I did have a Coke can and I had a Diet Coke can, and then I just had like a tank of water, like a container of water, and I put them in there. The Diet Coke will float, but the regular Coke will sink. Why do you think that would happen?
Because sugar.
It's the sugar. Okay, so which one has real sugar? The regular Coke. Do you know what Diet Coke has? You know what it's called? It's called aspartame. It's the same stuff that's in sweet milk. It's the same stuff that gives rats cancer when they give them like 500,000 times the normal human dose. So the Diet Coke has this fake sugar, and the regular Coca-Cola has something insane, like 44 grams of sugar. So which one is more dense?
The regular.
The regular Coke, which is why the regular Coke sinks and the Diet Coke floats. I've done this as a demonstration before. I just didn't think to go buy them from the store. And it just wants you to do it in a complete sense. If you can get it all in one, that would be fine. The assignment today is almost as easy as the one that was yesterday's, this one. And actually, you probably my paper copy. And hopefully you still have access to your periodic table. If not, you have an active link to one that's a PDF. This was, I don't know what this is. This was from yesterday. Gee, this was the skeleton and the sign. Right, in 1 minute, right? Oh, I'd have to go back and look. Oh, you did? Okay, then don't worry about it. If some of you were a little confused with the one that was yesterday's, I am looking for them today. But we will get through this fairly quickly. So some of you might just need me to literally, I'm not supposed to sit next to you, but show you like one-on-one where you're getting the information, Rosen, from the periodic table. So we're going to talk about, like I said, I call them isotopes. The more modern phrase for this is called a nuclide. They mean the same thing. They mean exactly the same thing. Well, there is one little exception. We'll get to that in a minute. Okay, but an isotope, the old term, the one that I am used to, first of all, you cannot change the protons. You change the protons, you change the element. And what tells you the number of protons no matter what? On here.
The atomic number.
The top number, the atomic number. And for right now, that number also tells you the number of electrons because we're talking about neutral elements. We're not making compounds yet. That will come later. So the P plus, this right here, is how I abbreviate proton. The E minus, because their electrons are negative, is how I represent the electrons. That is normal abbreviation. And then an N with a 0, which means it has no charge, is how we abbreviate a neutron. What's different with isotopes is they have different masses. Same element, so the proton can't change. They have different numbers of neutrons. You're still using a whole number for the mass. So these decimals on here, we're not using those. Still, we're not using the bottom number. We're using a whole mass number. Ah. And then they're going to be chemically alike because they have the same number of protons. You guys have that one on there. As long as they're the same element, they have the same chemical properties. What a nuclide or an isotope can do, if it has more neutrons than the normal state, those are the ones that have different nuclear properties. So the best one for me to give you an example is carbon-14. Carbon-12 is normal. Carbon-14 has what's called a half-life. And so it behaves like carbon, but its nucleus decays at a different rate. And we can measure that to figure out how long something's been dead. Not super dead, not like dinosaur dead, like Egyptian mummy dead. It has to have been sort of recently dead to be able to measure the amount of carbon-14 that's left. I can't remember if there's another bullet. I have 3 things in front of me. There's Earth space. So they're still chemically similar to their parent or the normal version of that particular atom. Now, a nuclide is a little different. Oh, do I have to put it here? Oh, it's further down on the bottom of this one. And so your atomic mass, your average atomic mass up there, they're decimals because it averages all of these isotopes or nuclides, whichever term you want to put there. A mass number, the one that we're dealing with right now, they're whole numbers because protons are worth 1 and neutrons are worth 1. Your mass number is a whole number. Your average atomic mass, for most of them, has a decimal. Like the average family has like 3.4 kids. And you're like, well, what's a 0.4 kid? It's because not every family has 3 kids. Some are like 9, they have 1. Some have 10. I went to high school with a girl, they had 12 kids in her family. All from the same mom and dad. But they also work on the farm. And that's normal. Nuclides. Nuclides is a nuclear species. Same elements, different numbers of neutrons. So nuclides of carbon, regular carbon's carbon 12. There's also a nuclide carbon 13, and there's also a nuclide carbon 14. The protons are the same, the electrons are the same, the neutrons are different. And I'm just used to calling these things isotopes because that's the way I was taught. I wasn't taught with the nuclide term. We're going to take a look at the isotopes of hydrogen. We talked about deuterium yesterday. Deuterium is the nuclide of hydrogen that they used to do atomic weapon research way back when in the day. It is not the one that was in the actual bombs. One was plutonium and the other one was, I can't remember what. Thorium, maybe? I'd have to cheat to look it up on my phone, but that's not important. That will be on your test. So you guys have something similar to this. Your image looks a little bit different, but regular hydrogen is on the left. And if you notice, the numbers are a little different on the side. So we have the symbol in the middle. We put the atomic number on the bottom, and we put the mass number on the top, so it's set up to subtract. So this has 1 proton, this has 1 electron. The mass is 1, 1 minus 1 is there's 0 neutrons in regular old hydrogen. We call this protium. It actually has a name besides hydrogen. Protium means 1, pro 1. And then next to it, we have deuterium, which is the one that we were talking about. DEU means 2. So the mass is 2. It still has an atomic number of 1. So it has 1 proton. They can't see me pointing online. It has 1 proton. It has 1 electron. And then 2 minus 1 is how many neutrons? 1. There's 2 things in the nucleus. So this puts the mass on the top. It's sort of reverse of what's on the periodic table. Puts the mass on the top, the atomic number on the bottom, so you subtract. Tritium doesn't happen in nature. It disintegrates almost instantly when we force it to be. Tri means 3. Like a tricycle has 3 wheels. The mass is 3, still has 1 proton, still has 1 electron, but how many neutrons does it have? 2. This is called isotope notation. You put the symbol down, put the mass top, atomic number bottom, so you can subtract. There's a different way that we can write this. Did I animate anything on this slide? I did. They all have 1 proton in common. They all have 1 electron in common. What is different is your number of neutrons. Yeah, I'll go back. Anybody needed that? You make a copy of that down. Like I said, we're still dealing with neutral elements, so your pluses and your minuses will be the same number for now. Eventually that will change. It's not going to change for a little bit. Now we have a messed up week next week, and we forgot that, well, first of all, there's no school for you guys on Monday. Then we have a work day. Well, now you guys are lucky. And then Wednesday, it's PSATs, and all of you will probably be taking the PSATs. So I will not see you Wednesday either. So we're trying to finish off this intro to the periodic table, the stuff we're doing right now, next week, but I don't know if the test is going to happen Friday. It might be the following Monday. I normally don't like doing that. We're building that section right now. We're trying to put stuff in the right spot. We'll get there eventually. All right, writing formulas for nuclides. This is what I just showed you on the previous slide. This is your symbol. There is no X element. There's an Xe, but there's no X by itself. So in the case of carbon 14, this would be a capital C. I bet you it will. Yeah, I don't see smart ink, so I'm not even going to try to write on the board. If it was carbon 14, this would be a capital C. This would be the mass, which is 14, and this would be the atomic number, which is 6. Carbon 14 has 8 neutrons. Regular carbon has 6 neutrons. Carbon 13 has 7 neutrons. It would be nice if I could write on the board, but I know full well if I do, it's not going to work right. And it looks like my aspect ratio reset. I'm going to wait till we're done creating master because it's going to put stuff in the center. It shouldn't be hanging off on the side like this. I think when the breaker failed the other day, that it reset my projector. I think. So carbon 14 and uranium 239, you know what, I actually need to be able to write on the board now. Let's see if I can get it to be better. Even though I just talked through this one, let's move this over here. Where's the smart ink? Where's it at? There it is. Where's that? Nope. Where'd it go? We're watching what happens if all the ice melts on Earth. How many cities would be swallowed up? It's not letting me pin it to it. Pin to there. Oh, I did animate it. All right, never mind. I knew this was going to be an issue, so I went ahead and animated it. This is pretty much how I'm going to end up having to do this in the future, because I get sick and tired of trying to write and it won't let me write. Carbon symbol is a capital C. And for those of you online, I'm holding up a periodic table, but carbon's right here. We use carbon all the time. You're going to memorize carbon whether you want to or not. Its mass is 14. You have to use the number I give you, not the number for the bottom number on here. You can get the atomic number from it though. So 14 goes on the top. The atomic number, which is 6, goes on the bottom. And then I believe I put on here the number of protons, neutrons, and electrons. Yes, I do. So carbon has 6 protons. Carbon has 6 electrons. Carbon 14, when you subtract them, has a total of 8 neutrons. There are 2 ways to write isotope notation. You can do it the long way, where you write out the name of the nuclide, you put a hyphen, and then the mass number. Or you can do it this way. You put the symbol with the mass on top and the atomic number on the bottom. They're both considered acceptable. Uranium-239 is the capital U. It's down on the bottom part. And it says that its mass is 239, but its atomic number is 92. So it does have 92 protons. And it has 92 electrons. How many neutrons does it have? What would you do to figure out the neutrons? Just subtract them. That's 147. There are multiple isotopes of uranium, one of which we use in nuclear power plants to produce energy. This is very, very similar to what we were doing yesterday. You just might have different isotopes. In fact, I think uranium was on yesterday's twice. There was uranium-235 and uranium-238 on your assignment paper. Are there any questions right now? This is sort of the easiest stuff that we do all year long. Like I said, you have to learn how to read this, or you're going to struggle. But protons, neutrons, and specifically valence electrons don't go away. All right, uranium-235. If we find uranium, which is the capital U, the same one we just did, Its atomic number was 92, so how many protons did it have?
92.
92. Oh, I need to draw on this, and it's not going to let me draw on it. Let's see if it'll let me do it this way. It won't. Even if I try to, it won't. I'm going to, I did on samarium, but I didn't do on this one. Okay, I'm gonna have to do this on the board. I'll talk through it for those of you that are online, because I'm just not fighting my board anymore. So uranium-235. Its protons were 92, which means how many electrons did it have?
80.
No. Electrons has to be the same.
92.
92, and then when I subtract them, what is it? 140, 143? Barium is Ba. 138. I have the fine barium, which is on the left-hand side. Its atomic number is 56. So it has 56 protons and 56 electrons, and when I subtract them, that's an 82 neutrons. You just have to use the mass number that I give you. Other than that, it's exactly what we were doing yesterday. Like you were still using the mass number that I provided you yesterday. Samarium, which is SM. Now, I'm telling you that samarium has 86 neutrons, that it has a specific number of neutrons. So you can look up the protons and you can look up the electrons. SM is in the bottom detached part, and it has 62 for both the protons and the electrons. And then the other one, osmium, says it has 111 neutrons, but we need to find OS. Where's it at? Right here. 76. So it will have 76 protons and 76 and 76 electrons. Now it says write the nuclide symbol and name. So samarium, since I'm just not fighting, I am not fighting my smarting. The total mass number would be what for samarium? Well, 86 is the number of neutrons. You have to add the neutrons. I don't have my calculator out to use my phone. 86, what did we say the atomic number was? SM 62? Okay, so the top number would be 148. And that would be right here. 148. And then the bottom number would be 62. That's one way to write it. SM 148 and then 62. There's another way to write this, and you would actually write out samarium. If it's in isotope notation, yes, you do. You put the mass on the top and you put the atomic number on the bottom. And those of you that are online, I'm sorry that my smart ink is not behaving. I can add them if you give me a second. Insert text box. So if I'm doing this properly, the top number was 148. Whoa, that is not what I meant to do. And then the bottom number drag it. It's not letting me grab it. It's not letting me grab it. If I could get this to shrink down, the one underneath it would be 62. And then the other way to write this would be this. So that is the other way to write this. I need to put in a new text box because it's not behaving to me. 62. I know y'all aren't used to making your own Google Slides, but this is how you do it. Those are the two ways to write it. Now, if I'm doing the osmium, then what did we say the number of protons was for osmium? I don't remember off the top. I don't know them all off the top of my head. 76. Which will go here. And then the top number, which would be 111 plus that, would be 187. I'm gonna double check my math. I don't math well. I don't math well in my head anymore. Calculators have ruined it. It's wrong way. And then if I was writing this out longhand, it would be osmium dash 187. So those are the two different ways that you would actually write these particular nuclides. All right, so the major difference between these, I mean, they really are the same generic thing. But the major difference between a nuclide and an isotope, which is the thing down on the bottom, they really mean the same thing. They're worded differently. Really, honestly, the only thing that's different is the grammar. They both are going to have this same element. So they're both going to have the same number of protons. They're both going to have the same number of electrons. They're both going to differ in the number of neutrons. It's this word species. Nuclides are a specific species. That means that they're all carbon's isotopes, or they're all oxygen's isotopes. They really do mean the same thing. It's just a different way to word it. And like I said, I don't care if you call them isotopes. That's what I'm used to calling these things. And there is an assignment that goes with this. You turn the light on. You double check the line. It's not very noise. I don't know if they're asking you a question or if somebody else just dinged in. Well, we have 15 minutes. If you guys are focused, you will not have homework. You will finish it in class. Okay, let me stop that.